Welcome to Thursday night pre-calculus. My name is Curtis Brown, and I've got Vicky Carter, Steve Kokoska, and Tom Dick here with me. We're going to be talking about those other trig functions tonight, other in quotes. Gotta love them. A lot of good stuff here. I know Steve and Vicky and Tom have put together a really nice set of materials for you. Which, by the way, if you open up the description for this video, down in the description, there are the questions in a link. Students, you can go and grab those and follow along as we're doing the session tonight. Otherwise, you guys can use them at your leisure. The other thing I will point out is that we will be putting the solutions up on this website or in this description here tomorrow morning sometime, maybe tomorrow afternoon, depending on how busy I get tomorrow. So, Steve, I think it's up to you to take us away, huh?
All right. Thank you very much, Curtis. Let's see if this is working. There we go. Let's try that. How about that? Can you see that screen?
I can.
Yeah, we can.
Yes,
Yeah.
Okay, very good. Great
I
to be
can.
back with you again, Curtis.
That looks an awful lot like my homework.
It does, with nothing written there. Wait a minute. Great to be
With
back.
nothing written.
Great to be back with the three of you again. We've got lots of questions for you, Curtis. I hope you've done your homework. I've been asking people to send you, please, to do your homework. We'll see what happens here. I think we do have some good questions here tonight, Curtis, and Tom's got some great calculator tips, and Vicky's insights are wonderful to have here along the way. So let's see what we can do with number one. We've got a couple of expressions here where we've involved trigonometric functions and inverse trig functions. And we're simply asked to simplify or evaluate these expressions. So the first one says the tangent of the arc cosine of 4/9. So I think there's some good conceptual things going on here. And then analytically, we're going to try to solve this expression. So the way that I think about this is the arc cosine, this expression right here inside those outermost parentheses, returns an angle. And what I have to do is to somehow figure out, well, what's the tangent of that angle? And so sort of the natural or problem-solving technique to get to an answer here is to start out by letting theta equal to the arc cosine of 4/9. Now, I didn't write this down, but this is your first homework question, Curtis. You might want to think a little bit about, well, where does theta lie in this circle, in this unit circle? What quadrant does it lie in? Now, I know it says down that an angle theta is in quadrant 1, but why is that? Can you give me any hint about that? Why is that? Why does theta have to lie in quadrant 1? How do I know that? Curtis, any ideas? You're right. Anything at all?
I was talking and you couldn't hear me.
No, I couldn't. I definitely couldn't.
I was doing my best. I was trying to help myself out there a little bit, give myself some time. No.
No, okay.
Looks to me like, go ahead.
Well, for the arc cosine function, it returns an angle by definition between 0 and pi. And in those two quadrants, where is the cosine of that angle positive? Well, that has to be in quadrant 1. So we have to think about, well, what is the range of the arc cosine? It's 0 to pi. And where is the cosine positive? It's in quadrant 1.
Right.
Now, there are two sort of ways that I think of for solving this problem, and Vicky has reminded me that in AP Pre-Calculus, sort of the main way that we're asking teachers and students to solve this, to think about a circle, think about quadrant 1, and draw this triangle. We know that we are in quadrant 1. We know that the cosine of theta is equal to 4/9. We know that that is x divided by r. I'll think of r as sort of the radius of that circle. Is that okay, Vicky? To think of it that way?
Yeah. And we think of x as the horizontal displacement. So
Very good. Okay. So I know that the cosine is the adjacent over the hypotenuse, or x over r. So I can place a 4 there and a 9 there for the radius of that circle. All right, Curtis, I'm going to give it a shot. How do I find this other side? How do I find the length of that side? What's the technique, or what theorem do I have to use?
Well, my son's just been working on this in his class there. And
Okay,
the Pythagorean theorem seems like a
good.
reasonable idea.
Sure. So I'm
But
going to write this a couple of times. Thanks, Curtis. I'm going to write this a couple of times. We're going to use the Pythagorean theorem that 4 squared plus this side y squared, whoops, I'm sorry, plus y squared is equal to 9 squared. So we know that y has got to be equal to the square root of 9 squared minus 4 squared. And if I've done everything correctly, that's the square root of 65. So I'll get to solving this problem in 1 second, but I want to arrow down just a little bit, see if this is working tonight. I want to come down here just a little bit. Another way to think about this is just to draw what I call a reference triangle. In calculus, we do this a lot, and I think that you can almost see this as sort of a, what's the right word here, Tom? Help me, an inset or an enlargement of what I have there. This is a reference triangle. I draw a right triangle, and I generally do this with the right angle over there on the bottom right-hand side, theta over here on the left-hand side. I know that x, this horizontal displacement, as Vicky calls it, is 4. The radius or the hypotenuse is 9. And similarly, I can use the Pythagorean theorem to find that that side y is the square root of 65. So look, either way, I end up with that vertical displacement as the square root of 65. I have a reference triangle down below. I have the circle and my lengths up above. How do I find the tangent now of theta? Cheapers, I got to arrow up again. Is that what I wanted? Yeah, I want the tangent. I'm going to rewrite this a little bit. I want the tangent of my angle theta. So as I arrow back down here, what's the tangent? Well, let's see. Let me think about that a little bit. That's the opposite over the adjacent, or Vicky, if it's okay to say, the vertical displacement over the horizontal displacement. So
Correct.
y divided by x, and that's simply the square root of 65 divided by 4. I could, if I wanted to, try to do some simplification here, but I don't think there is any. And I think in general, that's an acceptable answer. Vicky, and help me on this one. If this were a multiple choice problem, sometimes students might be asked to do some simplification because sometimes they have to work their answer into one of the solutions A, B, C, or D that's given. Is that correct? Is that
That
your?
is correct. Yeah. The only free response question that of course, the word simplification is never used, but there are several bullet points that describe how they have to present their answer, and that's going to be in FRQ 4.
Okay.
Um, but radicals are usually not the issue there. It's more of the I don't want to leave something as, for instance, 1 over cosine if I'm asked to express it in terms of secant theta or something like that.
Okay. Excellent. Let's take a
One
look
other
at the.
thing, real quick,
Right.
Steve.
I'm sorry. Sure.
Well, I mean, I can talk about it here or the other question. Students and teachers need to remember that both the expression arc cosine and cosine inverse with the little, what looks like the little -1 up in the superscript, those are equivalent ways of writing this, and students need to be aware of the fact that they may have to work with either one.
Mhm. If it's okay too, Vicky, I think a common error here is in writing this cosine like this, is some students interpret that as 1 divided by the cosine, and of course that's not true.
Yes.
This is our notation, our accepted notation for the arc cosine for the inverse cosine function. Yep,
Yes.
good
And
point.
both of the notations were used on FRQ 4 in 2024. One question had the arc, I can't remember which one it was, arc
Okay.
sine maybe, and the other had like inverse tangent. And I think the inverse tangent gave them a lot of trouble because they did interpret it the wrong way,
No kidding. Okay. Well, I think in these first couple of problems, I've been using arc cosine, arc sine, but
which
in
is
some of
fine.
the others, we'll use the other notation too. Okay. All right, let's take a look at part B, see what we can do here. Let me arrow up just a little bit, see if I can get that working. Beautiful. So this one has a variable in it, and it also has an extra 2 in it. Holy Toledo. So I want to find the cosine of 2 times the arctangent of t. So the arctangent of t is going to return an angle theta. And so another way that I can think about this is I've got to find the cosine of 2 theta. Yikes. Curtis, oh my gosh.
Cosine 2 theta.
Looking
That's
ahead. What am I going to
oh,
have
hold
to
on.
do here? What am I going to have to do down the line here eventually?
I need to apply some trig identity,
Okay, some
but I
trig
don't know
identity.
what
We'll give
one.
you credit for that one, Curtis. Okay, we'll give you
Give
credit.
me some credit for that one. I
Okay.
don't have that one. I don't have them all memorized.
All right, I'm going to start in the same way. I know that the arctangent or the tangent inverse returns an angle theta, so I'll let theta be equal to that tangent, pardon me, the arctangent of t. So the tangent of theta has to be equal to t, and I'll rewrite that as t over 1 because I'm sort of looking ahead here and I'm thinking about horizontal, vertical displacement. So I'll write that as t over 1. I should probably put a little bit more in here. I'm sorry that I didn't add this into the problem, but let's assume here that t is greater than 0, okay? I don't have a negative sign in here, so let's just assume that t is greater than 0. So, okay, I didn't write this in here, but this means that if t is greater than 0, the theta has to be in quadrant 1 again. Oh, no, Curtis. How the devil do I know that? Oh, no.
Say it again.
How do
I was
I know the theta has to be in quadrant 1 here?
you've got positives you've got it has well
Let's see. Well, what kind of
it's like
angles?
x
What kind of angles? What's the range of the arctan
of the
function?
arctangent got to be from well from 0 to, or from negative yeah, so it's got to be from 0 to 90, right?
It's got to be between minus pi over 2 and plus pi over
Yeah.
2.
Oh yeah, all those
And
radians.
and where is the tangent of theta positive? It's in the first quadrant.
In the first quadrant.
Having
Yeah.
a tough night here, Curtis.
Listen,
I'll throw you a couple softballs in a minute here.
I was just getting done helping my son with some homework, and it was not trigonometry, so
What's a
I'm
pretty sight?
gonna
Okay.
have to pass on that.
All right, so I've drawn this triangle with this circle. Let's see here. If I've got this right, the tangent of theta is y divided by x, vertical displacement divided by horizontal displacement. So here's my vertical, t. Here's my horizontal displacement, 1. I've got to find the length of this, well, what I'll call hypotenuse, or r. And again, using the Pythagorean theorem, that would be the square root of 1 squared 1 plus t squared. Beautiful. And just sort of for reference here, right below that, I've drawn my sort of equivalent reference triangle, the way that I would do that. So again, I draw this right triangle with theta over here on the left-hand side, right angle in the bottom right-hand side. I know that the horizontal length is 1, the vertical length is t. And again, by the Pythagorean theorem, I found the hypotenuse. So let's see here. Oh man, let's see. So I'm going to have to add in just a little bit. I'm going to have to think about this a little bit. Let's see, what's the cosine of theta? Well, the cosine of theta is, let's see, the adjacent divided by the hypotenuse, x divided by r. So in this case, that is 1 divided by the square root of 1 plus t squared. Beautiful. So I'm going to use that as I go to solve this expression from up above. Remember, we wanted the cosine of 2 theta. And okay, sorry about this, Curtis. Maybe I should put parentheses there. And let's see, if I remember correctly, there are actually 3 different forms of this trig identity. So I have to be, or I can be a little judicious in picking the one that I want. And it seems like this one, 2 times the cosine squared of theta minus 1, could be the best one, could be the most judicious, could be the easiest one to use. So here's my 2 out in front. The cosine of theta we have right here. I've got to square that, and don't forget the -1 on the end. And here I think there's a little bit of simplification that I can do. Let's see, I squared this out, so the square of the square root, I've got a 1 plus t squared down there in the denominator. The 2 is out in front, so that's not squared. That's in the numerator, -1. And in this step, all I did was get a common denominator, or write 1 as 1 plus t squared over 1 plus t squared, and did a little bit more simplification. And finally, I'm left with this expression on the end in terms of t. I like that problem. That's kind of cool. Is there any other simplification there? I feel like I want to factor that, but I don't think there's anything I can do. I can factor the numerator, but I can't do anything with the denominator. And so I think that's a pretty good form to leave that in. Vicky, Tom, any comments on that?
So one quick comment. So students are to know how to derive the double angle. We call it identity here for cosine 2 theta from their sum identities. So
Yes.
just telling students that if you forget the cosine 2 theta identity, you can always do cosine of theta plus theta and use your sum identity.
Okay.
I had a comment, Steve.
Sure, shoot.
So what if the t was negative? For
Oh,
example, what if you just flipped your triangle upside down across the x-axis so that you'd still have 1 on your adjacent side, I guess, but your t would now be a negative number. Yeah, exactly. I think this calculation still works just fine.
Okay, cool.
Because the cosine will still be 1 over the square root of the quantity 1 plus t squared.
Yes.
And when you put that into your cosine of 2 theta formula identity there, I think you just come up with exactly the same thing, even when t's negative. So,
Pretty cool.
yeah,
I like it. Pretty cool. All right, I think I have one more, Tom, if that's okay, before I hand it over to you for some technology. Let's see, the sine of 2 times the arctangent, yikes, of 2/3. So I'm going to rewrite this one just a little bit. So this time I've got the sine, and looking ahead just a little bit, of 2 theta. So Curtis, you know what I'm going to have to do here again. I'm going to have to use some sort of trig identity. And let's start this one just like we did the other two. We'll let theta be equal to the arctan of 2/3. So that says that the tangent of theta is 2/3. The tangent of theta is positive. So that means that theta, once again, must lie between 0 and pi over 2.
Agree.
So let's see if I've done this correctly here. If the tangent of theta is 2/3, that's vertical divided by horizontal displacement. I've drawn my circle, I've drawn my triangle. There's the vertical, there's the horizontal displacement. And now I've got to find that value for r, or the radius of that circle. So let's see, Pythagorean theorem. R would be equal to, well, let's see, it would be 2 squared plus 3 squared. 9 plus 4 would be the square root of 13. I'm going to write that in over here if it's okay. Beautiful. And just for completeness, just for the calculus side of me, I've drawn in that reference triangle down below also. I suspect, Vicky, and maybe I'm wrong, but I suspect that many of our AP pre-calculus teachers are also using that technique, drawing reference triangles from their calculus background. And let's put all of this together. Let's see. The sine of 2 theta, trigonometric identity, is 2 times the sine of theta times the cosine of theta. So let's see, the sine of theta, skipping just a little bit, that's the opposite over the hypotenuse, y divided by r, 2 divided by the square root of 13. The cosine would be the adjacent over the hypotenuse, horizontal displacement divided by r, 3 divided by the square root of 13. I was a little worried about this when I was multiplying all of this out. But let's see, that's 4 times 3 is 12, divided by 13, square root of 13 times the square root of 13. I think that's the answer, 12 divided by 13. Pretty cool. I was a little worried about this when I was doing it because I was looking at this real quickly and I said, oh, wait a minute here. Something's wrong. It looks like it's coming out to be a value greater than 1, but it isn't, and it better not be because we know that sine has to return a value between -1 and +1. Okay?
That was close, Steve.
Pretty close. Okay.
Close.
All right. Very good. Vicky, great comments. Tom, I'll turn it over to you for a little technology.
Okay.
There you go.
All right. So I'm bringing up my TI-84. I hope you all are able to see it okay. And so nice problem, Steve. I was going to take another look at your part B. That's the one where you actually had a variable.
Yeah.
B was in there. It was kind of a general thing. And so you're actually ending up with an equation that might be surprising. You had this one function that was a combination of a trig and inverse trig, different types, but it came out to be a rational function.
Rational function.
And when we come up with, and this would be true for anything that we call an identity, is a wonderful way to kind of check those is to graph the two functions and see if their graphs actually look the same. So that's what I thought I would try and do here.
Okay.
So I'm going to use x as a variable instead of t. But on your B, I think the function you started with was the cosine of 2 times the inverse tangent. You had arctan, but I'll be pulling up the inverse tangent symbol like this.
Okay.
And I'll use x instead of t. So there's that cosine of that. Let me just do a quick graph of that, see what it looks like. I'll do a zoom decimal. Oh, okay. Kind of interesting. So, well, yeah, it looks like it's defined for all real value. Well, that makes sense. The cosine is defined for all real values, so that as long as the arctangent is a real number, and it is, it looks good. Now, what you simplified this to didn't have any trig or inverse trig functions involved at all. I think
no, it did not.
Let's see. I think it ended up being 1 minus. Well, it was t squared. I'll use x again. 1 minus x squared. That quantity divided by 1 plus x squared. Okay. So are the graphs of these really the same? Well, let's take a look and see. All right. Wow, there you go. In fact, on the emulator version of the Smart View, it's so fast you think it would actually be just a little bit slower on the calculator, so you could actually see that red graph tracing right over the blue one. And if we actually bring up the trace, I can see now it's actually tracing on the blue graph, but the blue graph's covered by the red one. So for example, at x equal 0.6, I have this value y. Well, let me use the up arrow to switch to the other function. Exactly the same value. And that's going to be true for all values. So that's it's really a kind of nice way to do a graphical visual check of identities. Something that way back when I was learning trig identities, I didn't have that capability.
We couldn't do that.
Love the chance to graph these things and see, oh yeah, they really are the same. So, all right, I'll turn it back.
Oh, wait, Tom, don't leave that one. A couple questions here.
Sure.
So if we were to think of this as you have entered them as functions, then the original function that you entered on mine, cosine of 2 times the arctan of t.
Yep, there it is.
I think one good thing that teachers might have students do is to just think about what is really the domain of that function.
Mm-hmm.
And the very first thing you have to think about, I think, is, well, what's the domain of the arctan? What values can you plug in there? And in fact, you can plug in all reals. So you got to think a little bit about what does the arctan function look like, maybe? What's the domain of that? So now switch gears just a little bit and look at that rational function. And what's the domain of that rational function? It is indeed all reals, because there is no place where the denominator is 0. So here's a question. I wonder if there's some sort of problem that we could come up with a domain for the original and the domain for the, well, I'll call it simplified or evaluated expression is slightly different. We'll leave that as an open question. I'm sure Curtis will have an answer any moment now.
So
Okay.
Steve, something
Wow.
else.
Wow.
I
Something
know you
else.
will.
Teachers.
Amazing.
So another interesting thing is to think about the
Yeah.
range
Yeah.
of
Yeah.
this Y2
Oh, yes.
and
And
relate it
behavior.
back to what they learned in Unit 1 with rational functions
Yeah.
and in behavior,
Yep.
and where that maximum is occurring at x equals 0.
Yep.
I think it just makes it a very rich problem to spend some time on in the classroom.
Yeah. And can you students figure out what is the end behavior here? And can we do this, Vicky? Can we ask this? Write it mathematically with a limit symbol as x goes to
Could,
infinity, as x goes to minus infinity, right?
absolutely.
Yeah.
And at this point in Unit 3, not only do the students have the advantage of the rational function work that they did in Unit 1 within behavior, they
Yeah.
also now have that idea that sine and cosine, in this case cosine, has a range from -1 to 1. So it should give them like,
Yeah.
like a kind of see that relationship here.
Yeah. Hey, I think we just thought of a good question, Vicky.
I think
We
we
could
did
we
too.
could give students we could give students the original expression
Hmm.
and say describe the end behavior. Now, I don't think I
Yes.
could look at that original expression and know what it is.
No,
I would
probably not. Yes.
probably have to simplify it.
Right.
Yeah,
I love it.
I like it. I like it.
Thanks,
Okay.
Tom.
Yeah, sure. All right. Okay, I'll
Okay.
turn it back over to you.
Okay. Thanks, Tom. All right, here we go. Let's take a look at number 2. Beautiful. This one's kind of a quick one for me, Tom. It'll get back to you in a second, but I've got some TI-Nspire screens up here. This one says that the function f is defined to be, what is that? Minus the cotangent of that expression. I think it's 1/2 times the quantity x plus pi over 2, close parentheses there. And the first part of this just says sketch the graph of y equal f of x. So I know that you'll do this on the TI-84, Tom, maybe in a couple of different ways, but I did this on my TI-Nspire. This is kind of cool. You know that I really do enjoy using this machine. I can actually, on the left-hand side in the left-hand screen on a calculator page, I can actually define this function done in sort of a very natural way too, a way that I might write it with a piece of paper and a pencil. And then on the right-hand side on a graph screen, I've simply graphed this one. And what I tried to do is to pick some nice bounds, x min and x max, and some nice tick marks here. So I don't know if you can see this on the screen, but this is a pi over 4, and I've gone out to 2 pi out here and a minus 2 pi over there. I wanted to see if I could add in a couple of other things. Let me see. Is that pi over 2, 3 pi? So I think this is pi right there. And I think there's a 3 pi over 2 right there. That might come in handy. Okay. So there's a graph there. One thing here, and maybe Tom, you'll touch upon this. It kind of looks to me like there's some vertical asymptotes in here. It sure looks to me like there's some values of x where the function is increasing without bound from one side, decreasing without bound from the other side. It sure looks like there are some vertical asymptotes. So the first thing I'll think about is what's the period of the graph of f? Well, Vicky, help me on this one just a little bit. I think I can get this analytically by looking at the expression that was given to me. But might students be given a graph and asked to identify the period from the graph with appropriate tick marks and y mins, y maxes?
Yes, it's more likely it will be a sine or cosine graph, but
Yes.
yes.
Okay.
Um,
So
and
that is
obviously they need to be able to do it the way you have it in Part B also.
okay. So this is probably a little nerdy, but what I'm going to try to do here, sorry, I've got my little ruler. I'm going to try to draw in a couple of dashed lines. I don't know if that's working or not, but I see one there. And I think I see another one there. I see some vertical asymptotes there, and I can begin to see at least this graph sort of repeat. It might be a little difficult for me to be certain that the period is 2 pi from looking at that graph. What I might have to do is to expand my x min and my x max to be absolutely certain. Maybe go from minus 4 pi to plus 4 pi in appropriate intervals there. But I believe the period is 2 pi. And again, I think I can get that by looking at the graph, and I think I can also get that by using, well, simply the formula for the period, which is pi divided by or the absolute value of this coefficient out in front, which is 1/2. Beautiful.
Right. That was where my mind went immediately looking at your function going in. I was transformation of functions, thinking about, all right, I'm applying that 1/2 to that horizontal input.
Cool.
Right. So
Okay.
I'm
Yeah.
applying that kind of transformation. That was in my head, the 1/2 was going straight to the thinking about that as the over two, or sorry, the two
Related to the period. Yeah.
Right.
Okay.
I mean, it's a horizontal dilation by a factor of 2, and at this point,
right.
students should be, well aware that that's what's going on.
You should see that. Yeah.
Yeah.
Mhm.
So just something else I think that's kind of interesting that teachers can ask students here is, they should remember from the um essential knowledge statement in the CED for 311.A.5 that the graph of the cotangent function has vertical asymptotes for domain values where tangent is 0. I think Tom's going to show us a little bit with that graphically, but also that it's a decreasing function. Yet this looks like an increasing function. So what part of that function is telling us that the cotangent is changing from decreasing to increasing? So I think that's a good discussion again, to
Ooh,
go back
yeah.
and relate to the transformations in Unit 1.
Mhm.
Nice question, Vicky. I like
Yeah, I
that.
like it. And the last thing I asked about here is we're out of the vertical asymptotes on the graph of F, so I had to think a little bit about this. I had to look at the graph here. I've drawn in a couple. I think here's the way that I can write that in general. Sorry, minus pi over 2 plus or minus n, where n is an integer, times 2 pi, and I think I've got all of them. Good. Tom, I'm going to turn it over to you for a little technology.
Okay, sure.
All
Thanks,
right, there
Steve.
you go.
Okay. Uh, well, I'm going to go back to my y equals menu on the TI-84, and let me just clear out these functions that we had before. And what I wanted to do is just take a look at this graph that you were looking at. And the first thing that hit me here is I'm looking at my keyboard, and I've got sine and cosine and tangent. And above those, I have the inverses of those, but I don't have a cotangent key. Like you have on the Nspire, you can find cotangent under a menu. So I'm going to need to write cotangent in some other way. So what I'm going to do is show you the right way to do it. Okay, and I'll show you what happens if you try to take a shortcut. So let's see, we had a negative, so let me get the negative sign there. And the definition of cotangent of an angle is the cosine of that angle divided by the tangent of that, excuse me, divided by the sine of that angle. So let me do a cosine of that expression. Now I'll use 0.5 for 1/2.
Okay.
Times the quantity x plus pi over 2. Bear with me as I type that in. Okay, I think I got it.
So, Tom, while you're typing, so one of the things I would do as a teacher is challenge the students to actually really sketch this paper, pencil, graph paper, kind of think about the properties of the cotangent function, and then
Yeah.
put this in and check it with the calculator.
Yes, yeah, good point. Oops, I think I want to divide here instead of multiply by the sine of the same expression. So I'll do that 0.5 times the quantity x plus pi over 2. Okay. All right. Well, and for a window, why don't let me try one of this. Let me look under my Zoom windows here. Oh, number 7 there, Zoom Trig. Why don't we go down and use that? I think that's kind of optimized for functions like this.
Ooh, pretty cool.
Very nice, very nice. Okay. All right. And you can see it looks like it's crossing the x-axis right at some of these tick marks, but on your Zoom Trig window, if you trace over to one of those tick marks, you'll see that, well, you recognize that x value 1.5707. That looks like pi over 2. So the little hash marks here are spaced pi over 2 apart. On the y-axis, they are, I believe, is still like -4 to 4.
Yeah.
So this looks really good. You might have been thinking, well, instead of typing, I had to type that 0.5 times x plus pi over 2 quantity over twice because I had to do it both for the cosine and the sine. What if I had just done -1 divided by the tangent?
Seems reasonable.
It does, doesn't it? So 0.5 times, then I would have only had to type it in once. Okay, let's graph that.
The way he said
Bingo.
that sounded really suspicious.
Yeah.
Looks the same to me, Tom.
It does,
Oh,
doesn't
it
it?
looked like it went right over the top of it.
It looks like identical. So let's trace over again, this time on the red function.
You saved me some work.
And let's trace over to that first hash mark where that 0 was, at pi over 2. Oh, it's not quite at pi over 2 because pi over 2 is there. Let me try pi. Let me actually type in pi over 2.
Okay. Hey, there you go.
Ooh.
What happened there?
It says it's undefined. Well, does that mean the blue function is undefined? Let's just switch over to the blue function and type in pi over 2 for its trace value. Oh no, it's equal to 0. So at pi over 2, my negative cosine over sine version of negative cotangent is equal to 0. But my 1 over tangent is undefined. What's going on there? Well, 1 over tangent and cotangent, those two functions are equal to each other everywhere where they're both defined. But if one of them's defined and the other's not, bets are off. And that's what's happening here is 1 over tangent is also going to be undefined at those values where the tangent is equal to 0. And so that's the issue here. Now, if we went over to one of the asymptotes, I think from what you said, Steve, like
Yes.
3 pi over 2
Yeah,
would be
3 pi
that.
over
3
2.
pi over 2. Mm-hmm.
Now, let me put in 3 pi over 2. Okay, so the blue function, that's the cosine over sine version of cotangent. That's undefined. Well, that makes sense because there's a vertical asymptote there. And our other function, oh, I have to actually put in that 3 pi over 2 again because it kind of goes nearest pixel value. That's something I have.
Yeah.
3 pi over 2. Oh, they're both undefined there. So the vertical asymptotes for these two versions of the function are right on target, but we've got these extra undefined places when I tried to just go with 1 over tangent. Everywhere else, they're equal. But at those special values, they don't have the same domain. So the cosine over sine is the better way to express cotangent when you're on the graphing calculator. Now, Vicki, I was thinking, did you want me to show some other things here, or?
No, that's fine. The fact that you pointed out that the tick marks at those pi over 2 values, which actually correlates very nicely to what Steve was showing with the Inspire, because he had the tick marks set, I think, at pi over 2, didn't you, Steve?
I think I had them pi over
Pi,
4, units
pi
of
over
pi over
4.
4.
Okay.
Yeah. Yeah. Yeah.
So either way, we can kind of see, but it should be pretty obvious to the students that you've got the vertical asymptotes happening. You've got the one at negative pi over 2 and then the 3 pi over 2. So again, we can go back to that thinking about the period that it's 2 pi, just some things like that. But it shows it nicely here. That was all.
Okay,
Tom,
great.
one more question. You don't have to do this. You don't have
Sure.
to, but if we were just dealing with the red curve that you have up there now.
Hmm.
So suppose we ask students, let's sketch that graph. So what's the characteristic of the graph that's going on at pi over 2? What does that graph have? And we're not talking about vertical asymptote, but what's going on? What's the characteristic in that graph, Curtis? At pi over 2?
At pi over 2,
Yeah.
the characteristic on this particular graph,
Yeah.
pi over
So
2.
I'll go ahead and go
Tom,
there for you so you can see.
so
Jump me back there. So so you guys catch me every time when I'm looking at something else. This is like when your teacher says, this is like when your teacher grabs your attention, that kid's not paying attention. I'm gonna call on him. No, I'm looking at that and I'm thinking, boy, there's an x-intercept that's happening there in the blue graph that Tom had up there, right? We had the numerator equal to 0, the denominator equal to 1. So in this situation, you now have a hole there,
yeah,
right? It's undefined
yeah,
because at that moment we have a problem.
very good. So Tom, you and I have talked about this a couple of times. I don't want to make you try to do this, but just off the top of your head, is there a way to show that hole on the graph of the red curve? I mean, I can think about showing a hole if I had a hole, if I had a hole
Well,
in the graph at an integer or, maybe at a nice rational number, I might be able to do it. But here it's irrational. So I'm not sure if you can do that easily.
Yeah, I'm not. Yeah, in fact, I mean, I'm able to look at it close enough here. I don't know if it's showing for you
Yeah.
guys, but there
I
is,
can
even though
see
it's
the red.
crossing the x-axis there, I
Yeah,
can tell there's a pixel, there's a red pixel there. So
yeah.
we're not
Tom,
seeing a hole. It might
try
be really
something.
tough here because these are happening at irrational values. That's the,
Hey, Tom,
yeah,
try something for me.
all
Try
right.
something. In the window,
Mhm.
Okay.
set your x min to like negative whatever that first asymptote
Go
is.
to
Was it
minus
negative
pi over 2 to 3 pi over 2,
Yeah.
Tom.
Okay. Negative pi over.
minus pi over 2? Just put negative pi over 2 there
Okay.
and hit enter.
Okay.
And then arrow down to the delta x, or sorry, the trace step rather, and put I don't know, some multiple of pi over 2 that we can get a nice one. Maybe pi over 24.
Sure.
That's going to shrink everything down, so we won't be seeing all kinds of stuff. But now go back to your graph, and maybe we'll get a spot where we can see that hole pop up. I was trying to get those to land on pi over 2 increments. Now that first uh, that first tick mark should potentially have the hole there. But I think I can see the red, so I
Yeah.
don't think it worked. Um,
And try one other thing, Tom. If you keep the same y min, but make y max 3 pi over 2.
yeah.
Yeah, I think we just miss it.
Yeah, it's
Yeah.
really, really
Even with
close.
that was a good try, but I think that we're just off just enough that
Go up to, yeah, do what Steve said and try changing it to the um
Go
X
back to
max to
window.
3 pi,
three.
go negative pi over 2 to 3 pi over 2.
So make it
Okay.
3 pi over 2.
And that might get us better because it's a close enough.
All right.
Yeah, just try
Maybe a
that.
small enough trace step to see. No, it
Not
hit it.
really.
Yeah, it's still, yeah.
I hit it.
Yeah, I
Mouse a
think it's
little bit,
tough
yeah.
with
Yeah,
those
I don't think
irrational.
there's a way you can get it small enough.
Yeah.
So we'll leave that as a challenge question, Curtis, for the technology wizards out there. How can you get that hole in that graph? I like it. I like it.
All right. Okay.
Thanks,
All
Tom.
right. I'll stop the share and turn it back over to you.
Okay. All right. Thanks, Tom. Cool stuff. All right. So I've got a technology problem here. Tom will try a couple things on the 84 again. I'm going to try to solve this on the TI-Nspire. So this one is a sort of an applied problem using technology. This time, the amount of water in thousands of gallons used at a certain facility, manufacturing facility, during a 24-hour period is modeled by this function. It's got an inverse tangent in it and a crazy argument there, 0.025 t squared. And we'll assume here that t is measured in hours from 0 to 24. So this is over a day, let's suppose. So using this model, how much water did the facility use during the 24-hour period? Remember, F returns the cumulative amount of water that they have used, the total amount of water that they've used at time t. So this is sort of a basic problem where students have to use technology. There's a little bit of conceptual, little bit of a couple of ideas going on here in the background, but they've got to use that technology to define the function and evaluate the function. Here's a couple of ways to do this on the Inspire. So once again, I defined my function f, there it is. And once I've done that on the Inspire, I can simply evaluate that function f at 24, and there it is, 9.362 thousandths of gallons of water. Now, one little thing here, Curtis, I have my TI-Nspire set to return 3 digits to the right of the decimal because in general, that's what we want on the exam. That's what we want from our students. We worry about 3 digits to the right. And on the right-hand side here, just a double check, and just because I wanted to see what the graph of that function looked like, I graphed f, and I kind of picked an appropriate range there, x min to x max, 0 to 24. And I've forgotten what I went to. I think I went something like -2 to 12. I know that there are no negative values for f, but I wanted to move that x-axis, that horizontal axis, up a little so that you could see it. And then what I did on the Inspire was simply evaluate that function at 24, find a point on the graph where t or x here is equal to 24. Did I get the same answer? I did, 9.362. I feel pretty good about this one. Kind of cool.
So if students are wondering about, could there be a question like this on the AP exam? Definitely in the calculator part of the multiple choice question. So you're going to see 4 choices there. Basically, it's about reading carefully and entering your function carefully to make sure you're using the correct functions. Like you've got to use the inverse tangent and not
Yep.
tangent, this kind of a thing. And do you know what you're looking for? In this case, what you said, Steve, that I need to evaluate the function at 24 in
Yeah.
order to get the correct answer. So there are going to be some other answers that are other weird things that you might do to this question if you don't really understand what it's talking about. And you would get some of those, what we call distractors.
Yeah, and not you have to know to evaluate the function at 24, as you said, not set this function equal to
Equal to
24. So
24, yeah.
not
Or
write this as 1 divided by the tangent. And
exactly.
Vicky, I had another question for you. Oh yeah. So all right, suppose this were on the calculator active portion of multiple choice.
Uh-huh.
But these values up here, the 0.25025 and the 6.235, let's suppose those were not integers, but
Closer.
non-decimal, not
Okay.
decimal.
Okay.
So if those weren't decimals, and I'm using a CAS machine, it is possible that that comes out to be symbolic.
Right.
And
And
so you have to know here to convert that, right,
yes,
from the symbolic
yes,
analytical answer into a decimal approximation. Yeah.
right. That is correct.
Okay.
So of course, we've talked about tricks with that in previous webinars and things, but you might want to ask your teacher if you aren't sure, but there's an easy way to do it on a CAS machine to get that decimal response.
Yes. A couple of easy ways. Yep, absolutely. So, all right, using this model, excuse me, at what time T did this facility, this manufacturing facility, use half of the water used during the entire 24-hour period? Well, I know that they use 9.362. I know it's in thousands of gallons here, but let's just say 9.362. So I have to solve this expression for T. So that's sort of the concept here. I have to solve this expression for T. Now, one minor issue here, well, maybe not minor, important issue here is I have to use that 9.362 to the greatest degree of accuracy that the calculator can use or can store. So here's what I did on the TI-Nspire. I actually did this in a couple of different ways to check myself, and Tom will have a way to do this to show you on the TI-84. I let G, a variable G, be equal to f of 24 divided by 2. F of 24 is the total amount of water used by the facility in, well, the 24-hour period. And I have to find, well, when did it use half of that amount of water? So I took that total amount divided by 2. I've got a 4.681. Now, that's the way it displays on the screen. But remember, it's stored much more accurately in the calculator. G has a much more accurate representation in the background on the calculator. Now, there are a couple of different functions that I could use on the TI-Nspire. Tom knows that I like to use the function zeros. So I'm going to find where f of t minus g is equal to 0. So I'm actually solving this expression, f of t equal to g, which is my f of 24 divided by 2. And on the Inspire, you can see I gave a little bit of extra condition to this. That vertical bar in my mind stands for such that. So solve this, find these zeros such that or so that t is between 0 and 24. So the way that I've set this up, the TI-Nspire will come back with a list of answers, and it comes back with only one, 6.109, which is pretty cool. I think sort of a natural wrong answer to this is, Vicky, help me on this, is that students might think, well, it just naturally uses half the water at half the time. And
Yeah,
so 12 is going to be a distractor for
yeah.
sure in this kind of a problem. Okay.
Yeah, and I do want to assure teachers and students that there will not be a multi-step problem like this will not be in the free response question. What we're really trying to make you understand is that in part A, you had to find a value of the function, whereas in part B, you've got to solve for a given value, even though it happened to be something we worked with in the previous part. But there it was to kind of show you that how you could do things wrong and get an answer that would be one of the distractors.
So, and you might see a question like, well, at what time did they use 5,000 gallons of water?
Right,
And you
right.
have to find that value of T. Gotcha.
Exactly.
Gotcha.
Yes.
So here's another way that I could solve this actually on the graph screen, and I know a lot of people like to do it this way. Here, if you can see the colors, Curtis, this blue curve here is a graph of f, and this green graph is a graph of, well, just a horizontal line or just a graph of the constant function g for y equal 4.681. And what I did on my Inspire is I found the point of intersection of those two graphs. So it happens at time 6.109. Did I get the same answer I did there? I feel pretty good about this one. I think I've got this one right.
Yeah, and another part of
Oh, I'm sorry.
contextual problems like this is making sure you know what the x-axis represents and what the y-axis represents. So when you get that ordered pair, what does the 6.109 represent? What does the 4.681 represent? So it's all about practicing these contextual types of problems with your calculator.
I'd like to also add a little bit here, Vicky, about communication. If this were on a free response portion of the exam,
Well, it won't be.
well, one common error we see is the reporting of ordered pairs
Yeah.
rather than just the correct coordinate.
Correct, especially with contextual problems. And students need to keep in mind that we were talking about thousands of gallons of water. So, you know, that, and there has been one similar to that.
Okay. Cool. Tom, can you finish up with a little technology?
Sure, Steve. Yeah,
Okay, there you go.
take a quick look. And
While Tom is booting that up, I was able to make that that whole show.
Oh, cool.
oh, we're impressed, but I'm not sure we believe you, Curtis.
It took a little bit of work.
No, that's great. We'll have to compare notes.
I basically had to put in an X minimum that was pi over 512,
Okay.
smaller than the whole, and then do pi plus or sorry, the whole value plus 5 pi over 512.
Oh, okay.
So
So essentially you
my
zoomed in.
boundaries were this close.
All right.
And that got those pixel values small enough that sure enough it hit a pixel.
Wow. Interesting. All right, Tom. What do you get?
That may have been excessive, but it didn't work.
Well, on this last problem Steve did, I was just going to show on 84, but also give a little bit of advice of some kind of efficient calculator usage here. So I had already entered the function using x again instead of t for the variable. There it is. That's the function, our model. And let's see, in terms of a window for graphing, we're given a domain for this. So it's from 0 to 24. So let me just enter that as my x min and x max. And I might not be sure kind of what to use for a y range. But if you go to your zoom menu and you scroll down to first one past that first page, it says zoom fit, it'll actually sample and come up with a y range that'll be reasonable. So let's give that a shot. Oh man, it's great. It actually, not an accident, it pretty much fills up the screen vertically.
Yep. Cool.
So there's a nice graph. If we trace it, we can go to particular values. And the one value that was of specific interest was that, what's that n value at x equal 24? So let's trace over to there. Okay. Well, there's that y value that Steve got.
Mm-hmm.
And just another note, when you trace, if you go back to your calculator screen, so I'm going to quit, the last x and y values of the point you were on tracing are stored right now in x and y. So if I was to call up y, there's that value. And we needed to take half of that. So let me divide that by 2. And rather than copy this down, let me just store that. I'm going to use h for half. That's half of what we okay. And then when I go back to y equals, I'll just plot the constant function y2 equals h.
Cool.
That's that value that we just stored away.
Yep.
And when I graph, oh, looks a lot like Steve's graph. We see that horizontal line, and we need an intersection of those two. So I'll do my calc menu. There's number 5, intersect. And the first curve, well, the blue one, we only have 2 curves. So those will be the 2 we'll do. And a guess, well, I'm counting 1, 2, 3, 4. Looks like somewhere, is it somewhere around 4? I'll put in
those tick marks were.
Oh, those might not be integers. Well, I'll put in 4 anyway and see what it gives me. Ah, there we go. 6 points. Yes, those tick marks are definitely something different. So 6.10
109.
is
Yep,
going to
right.
be rounded to 6.109. Looks
Yep,
good.
right on the money.
We got it.
Hey, Tom,
Yeah.
is there is there any reason not to use the numeric solver for that?
There's no reason other than I'm a
You don't
graph
have
I'm a graph
graphical.
junkie, Curtis. I love to use graphs.
I love the
love
graph. I love the graph too.
Yeah.
I
I can
do.
see what I'm
I love the
doing,
graph too.
and I'm reassured by
I
what
love
I'm
the
looking
graph
at.
too. Conceptually, I think it's an important thing to do to see the graph. Was thinking about efficiency. You stored that to H. That's that half value to H, right? Um, and you can now just set Y1 equal to H.
Exactly. Yeah.
And
Yeah.
the numeric
I'm not.
solver.
I'm not saying that that wouldn't be a good way to do it too, Chris. It's just I tend to these kind of equations. I tend to like to calculate them right off the graph because I'm looking
Yeah.
for that kind of visual
I like the
reassurance.
visual confirmation too, for sure. I was just thinking about other ways to do it, and I know not a lot of folks know about or even utilize that numeric solver. So
Okay. So in the future, I will make a point of find that out.
that is not a
No, it's a wonderful tool. So
so
all
anyway,
right,
that
well,
was the
let me
thought.
stop and
All right, very good, Curtis. Nice work tonight.
Well, I didn't do a whole lot tonight. Uh, Clearly, I didn't do my homework. It takes me a little while to warm up to doing a little bit of mathematics. That's all right. Uh, I got a little bit of help in the chat tonight, so that was good. People helping me out.
Good.
And we had a nice investigation in the trying to make that whole Explorer.
cool.
Oh, good. Very good.
So anyway, I'll put my email in the chat tonight. If anybody is out there needing professional development certificates, I'm certainly happy to send you a link for that. I also know that here in not a very long time, we'll be posting the problems for the next round of this, which should be, what is that, March? Is it right? Exactly 28
March
days?
13th. Yes,
13.
So
March
it's
13th.
March 13th. I thought it was March 13th. I didn't want to overpromise and underdeliver, but I figured it was March 13th. So yeah, we'll look forward to hosting another one of these here in about a month, and maybe this time around I'll do my homework.
Well, the next one is on some polar stuff. So
Oh, that'll be really fun.
That'll be
yes.
cool.
Oh man.
I'm sorry I couldn't.
All right. On that note, we'll see you all soon. And I'll put my email in the chat.
Very good.
Bye, everybody.
Thanks,
Bye.
Chris.